All right, in chapter 6.3, we're going to be talking about binomial and geometric random variables. Okay, so we're going to determine if the conditions for using a binomial distribution have been met, and compute and interpret probabilities involving binomial distributions, and then calculate the mean and standard deviation of a binomial distribution. And then in part 2, you're going to find probabilities involving geometric random variables. So this is focusing on binomial distributions. So basically they're used to test whether, like for example, if you wanted to test whether someone has extrasensory perception, ESP, you would choose, say, one of these 4 cards and identify the card without seeing this. And you would do it 50 times to see how many times the person identifies it correctly. And so your outcome of interest is to identify correctly. This is where it gets into binomial. It's either going to be correct or wrong. Success or failure. And so there's going to be 2 options, right? And so the random variable would be the number of correct identifications. All right, another game is Pass the Pigs. Is a game where you actually roll dice that are pig-shaped. And you earn points according to how the pigs land. So your outcome of interest would be pig out, which means you lose points for that round. So your T, or your random variable, is the number of rolls until the player gets a pig out. Okay, and then the last one is a shipping company claims that 90% of its shipments arrive on time. To test this claim, you take a random sample of 100 shipments and you see how many arrived on time. So it's either on time or your other would be late. And so your random variable would be the number of shipments on time. Now the one that is not a binomial, and we're going to talk about that now, is the second one, because you need to have an exact number of trials. And in this case, it's saying you're going to roll until the player gets a pig out. That's not okay, unless you said you're going to roll 50 times and see how many pig outs you get. Okay, so this is the only example that is not binomial. We're going to talk about how this is geometric at another time in the next video. So to determine whether you have a binomial versus a geometric setting is you look at bins. Bins is the way you test for binomial. So the first thing you're going to ask yourself, is it binary? Can it be classified as win or lose, success or failure, so on and so forth? Is it independent? That's one trial doesn't affect another trial. So that's like rolling a dice or flipping a coin. Versus if you select cards from a deck, you have to replace the card. If you don't replace the card, then it's not independent anymore. And then number is a number of fixed trials. So that means you're going to do something 10 times, 20 times, so on and so forth. And then success is the probability of success. So you need to have that or be able to calculate that as well. All right, so we're going to look at a couple cases and see, is this considered a binomial distribution? So in case 1, it says genetics says that children receive genes from each of their parents independently. Each child has a particular set of parents and has a 25% chance of receiving type O blood. Suppose these parents have 5 children, and let X equal the number with type O blood. So in this case, your binary is type O and or other. So it's type O or not type O, right? It is independent because it doesn't matter if the child number 1 had type O, it's not going to affect whether or not child number 2 is going to have type O. And then the number of trials, well, in this case we have 5 children. And then the success probability is 0.25. So this would be for a success or type O. And it would be 0.75 for not type O. And the reason I knew that is because your probability is always going to add to 1. All right, so let's look at the second situation. It says shuffle a deck of cards, turn over the first 10 cards, and determine whether or not the number of aces you observe. Well, the problem with this is that it's not going to be independent. And the reason it's not independent is because you're not replacing the cards. And so therefore this is not, case 2 is not going to be a binomial. All right, let's look at the third example. And this, you're looking at cards again. You're going to turn over, but you're putting the card back and shuffling again. So this would be an example of bins. So B is getting an ace, or no, or not, right? And then I is, because it's replaced, that's a yes. N is, ooh, but look here. It says, repeat this process until you get an ace. So because there is no set trials, no set number of trials, this is not binary either. Okay, but your success, you could figure that out. It would be 4 out of 52. That's 4 out of 52 would be your success rate, and then your failure rate would be 48 out of 52. So moving on. All right, so let's look at case 1, because that was the only one that was binary. Suppose you want to know the probability that none of the 5 children have type O blood. So basically, the probability of not having type O blood is the probability of complete failure. And so you simply just take 0.75 and raise it to the 5th power. And so when you do that, type in 0.75 raised to the 5th, you get 23.7. Or 0.237. Which means there's about a 24% chance that a child would have zero of the 5 children would have type O blood. All right, so what if we want to know the probability that one person is going to have type O blood? Well, now you have to look at the success of type O blood is 0.25, so that's going to be raised to the 1, right? And then the percent of failure, or not type O blood, is going to be the other 4 children. But you also have to take into account that there are 5 outcomes. So it could be the first child that has type O blood, the second, third, fourth, or 5th. So you do have to multiply by the total number of outcomes as well. And so when we set this up and type this into our calculator, we're actually going to type in 5 times 0.25 times 0.75 raised to the 4th power. And you actually end up with 0.3955, right? Or we can say 39.6% of the time, at least one child is going to have type O blood. Right? Now, if you wanted the probability of 2 children, again, to set up the probability, you know that you're going to have 2 successes and 3 failures, right? However, you need to know your number of outcomes. So if you list all your number of outcomes, you could have the first 2 children having type O, the first and the third, so on and so forth. So this is where your tree diagram would come into account. Or you know that you've got 5 kids times 2, which gives you 10. So you're going to have 10 possible outcomes, which is where this comes in here. And then you're going to multiply it by the percent of success times 2, raised to the 2. So 10 times 0.25 raised to the 2nd times, 0.75 raised to the 3rd. Don't forget to scroll over. So this is equal to 0.264 or 26.4%. So if you can make a tree diagram to list your possible outcomes, but you can also use factorial. So you would do like 5 choose 2. So this is NCR. So if you want to do it on your calculator, it's NCR. You should remember this from Algebra 2. So if I had 5 possible outcomes, I would type in my calculator 5, then I would go to math, Scroll over to probability, go down to NCR, and hit in a 2, hit enter, and it should come out as 10. So please remember this is under math, and then probability, PR. And I think it's number 3. All right. So if you want to do 5, choose 3, you can do the same thing. Type in 5, math, scroll over to probability, go down to NCR, 3, hit enter, and again you get 10 possible outcomes. So, and then you would raise the percent of success to the number in question, and then failure would be the other 2. So when you multiply all that out, you get 10 times 0.25 raised to the 3rd, scroll over, times 0.75 raised to the 2, and you end up with 0.088. So really there's only like a 9% chance that you'll have 3 kids with type O blood. Okay, so now we're going to talk about how we can find the mean and the standard deviation. But I'm going to put this video on pause for a second. You're going to have to do part 2 because I'm going to run out of time.